Hi everyone. So last time we were working on vertical asymptotes. Today we're going to go into horizontal asymptotes. Now, let me go ahead and just quickly review what we're talking about vertical asymptotes, and then that will lead us to what we're doing today. We talked about our graphs. Specific graphs, what we call rational graphs. And rational graphs are fraction graphs, okay? Fraction graphs. These fraction graphs look like, for instance, I see 1 over x plus 1. And we talked about what value is not allowed here. Now, in a regular polynomial, x squared plus 2x plus 1, you can plug in any number you want from negative infinity all the way to infinity, and you'll receive just a number as an answer. And that's perfectly fine. Polynomials look like this. For every x value, you have a nice y value attached, and we're cool. But when we're dividing, we had a rule since Algebra 1. We cannot divide by what special number? By 0. You cannot divide by 0. And that was a big deal. If I try dividing by 0, we end up breaking the laws of reality. And we said the dividing by 0 gives us what we call a undefined. Undefined means it's not labeled. There's no answer for it. It is not in our playground. It's undefined. Right? How's the relationship? It's undefined. You don't want to hear that ever, guys. Okay. All right. So we have a function here. F of x is equal to 1 over x plus 1. And we have a value where x is equal to negative 1. If x was negative 1, we would have an undefined value. This would go to 0. Y would be undefined. Undefined. So that led us to say, you know what? These are what we call vertical asymptotes. And on a graph, it actually led us to say, you know what? If it's undefined, we have a vertical asymptote. So I draw this using dotted lines to say, hey, we're not allowed to touch that line. It's almost, again, like you being a little kid and your parents don't touch that. And you're like, touch what? Touch this? And you get spanked. So we're not allowed to touch this dotted line. We can play around it. We can do whatever we want around it, wherever it goes, but we are not allowed to touch that line. Okay. Sorry, I'm jumping around, adding letting people in. Okay. So now how does this graph work? I'm going to go ahead and plug in values on the right. So 1 over x plus 1 on the right, 1 over x plus 1 on my left, and we're going to plug in numbers on the right side. And you can see the numbers are going to be 0, 1, comma 2, right? We'll plug in these three numbers into the problem x, and we'll see where that goes. So I'll draw a little table here just for us to illustrate what's going on. This is, again, our f of x function. So f of x, if I plug in x is 0, 1, and 2, we'll take a look what that looks like. If I plug in 0, 1 over 0 plus 1, 1 over 1 plus 1, 1 over 1 plus, 2 plus 1, I'm sorry. And you'll see something interesting about the numbers. The first answer is 1. Next answer is 1 over 2, and the next answer is 1 over 3. What do you think happens as x gets bigger? What if I plug in 10 here? 1 over 10 plus 1 is 1 over 11. Is 1 over 11 a big number or a small number? It is a tiny number. So as x gets bigger, our y values get smaller. Because this is division and our variable is on the denominator, the larger number that we put up, the smaller our answer is going to be. It's almost like having more mouths to feed. If it's you yourself, 1 divided by 1, you get all your money. If you're married, that's 1 over 2. Man, you got half your money now. What if you have a kid, married and a kid? That's 1 over 3. You get a third of your money. Oh my gosh, you're losing your money. What if you have 5 kids plus a wife? That's 1 over 6. You're even more poor. So the idea here is that this value gets closer to 0. Closer to 0. What happens on the left side, though? Is the left side going to imitate the right? And the answer here for this specific problem is no. Now, just like us graphing polynomials, we'll see certain characteristics that we can apply here, so we don't have to do all the quote-unquote work. So here we go. That's the on the left side. But we want to do it right now for our first couple of problems. And I'm going to give you guys a f of x. And we're going to plug in numbers on the left side here. We can't plug in -1. Remember, we can't plug in -1. But we sure can plug in -2. and negative 3, and negative 4. So negative 2, negative 3, and negative 4. We said we can't plug in negative 1 because that would be undefined, and we're not allowed to touch that. We're not allowed to graph there. So 1 over negative 2 plus 1. 1 over negative 3 plus 1. 1 over negative 4 plus 1. And you'll see something kind of interesting because these answers will mimic those on the right side, except negative 2 plus 1 is a negative 1. So negative 1 over 1. Negative 3 minus 1 is negative 2. Negative 1 over 2. Negative 4 plus 1 is negative 3. 1 over negative 3. And if you look here, these answers are exactly the same, except now not positive, but negative. And these graphs, this value will go like this. What happens as we approach 0 as x equals to negative 1? The f value on the right side, so I'm going to put a little plus sign here. This is our notation. Plus sign means this is going to shoot off to infinity, positive infinity. But on the left side, as x approaches negative 1, from the left side, f of x goes to negative infinity. Right, is going to hell. And that's why we can't graph it at negative 1. We would be dividing by 0, which really meant it's undefined because it goes to infinity, and infinity is not a number. Okay, great. But is it really going to take me this much work every single time I do a problem? And the answer, like I normally tell you, is no. Answer is no. But before we get to the no part, we want to find out some more characteristics. Like one, how did I know, Michiko, how did you know that this graph was going to flatten out? The right side was going to flatten out at 0, left side was going to flatten out at 0. And that's what today we're going to discuss is our horizontal asymptote. And the horizontal asymptote rule is straight memorization. We'll talk about why. In the long run, we could figure out, we come up with the rules, meaningful reason why it's like this. But right now we're going to start off with just memorizing the 3 rules that define our horizontal asymptote. Here we go. So today's, what we're working on is horizontal asymptotes. How do we know that this graph is going to stay at 0 here? How do we know this is going to be stuck there? Horizontal asymptotes. And a horizontal asymptote is the line at which the graph will get stuck. See, I'm stuck now, getting closer to 0. On the left side here, I'm getting stuck at y is equal to 0. Okay, we're just getting stuck here. And that's our horizontal asymptote. And I will graph this with another dotted line. Let me do a dotted line here. Dot, 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 dot. It's almost like a boundary, okay? And this boundary, we're going to, at infinity, almost become it. Okay, so here we go. So how do we come up with a horizontal asymptotes? Now, let me give you a reason why we want to find out our horizontal asymptotes. Okay, imagine if I give you the graph is 1 over x plus 2, x minus 2, and ask you to graph this. Do you really want to come up with a table of x's and y's and plug in all these random numbers in here? And the answer is no way. We do not want to do this. You would cry if you had to do this for every single problem in the world. Instead, we're going to talk about some characteristics about this graph. That's first always find. First, always find your vertical asymptotes. So step 1, find your vertical asymptotes. And since this graph is already factored, we can tell when our denominator, so I'm going to use the letter d here, when is d of x equal to 0? At what values are the denominator going to go 0? So when does x plus 2 equal to 0? And when does x minus 2 equal to 0? We see that x can be negative 2 and x can be positive 2. And if we tried negative 2, positive 2, we would divide by 0. So these are our vertical asymptotes for us. Okay, so if I go ahead and try graphing this, at negative 2 and positive 2, we have these graphs of these dotted lines, which break up the graph into 3 different parts. 1, 2, 3. Now, in these 3 different parts, how is the graph going to behave? And here's my answer to you. We don't know yet. We could plug in values and we can see maybe it looks like this, but as of right now, what if this graph was up here? Maybe everything is up here. Maybe it's on the bottom. How do I know it's not flipped over and we're not down here? There's too many possibilities for us. So we're going to do our next thing, and we're going to look for step 2, horizontal asymptotes. The horizontal asymptote for this, I can automatically tell you y is equal to 0. What I mean by y is equal to 0 is that at the end behavior, remember how we talked about end behavior, where this graph will eventually head? So we graphed already. Let's regraph this. I'm going to graph this a couple times. We graphed at -2, or is it positive 2, and -2. I'm going to give you one more step here, that we have our horizontal asymptote is at 0. So I'm going to go ahead and graph right here, horizontal asymptote at 0. So I'm actually going to make a dotted line right at 0. Now what does that mean? It means as the graph heads to negative infinity, we are going to get stuck at 0. As I head to the positive infinity, we're going to get stuck at 0. Well, it could also be this way or this way. But here is the key point. The key point is that we are headed toward 0 at the end. What if this horizontal asymptote was at 1? Okay, if y is equal to 1. If I draw the graph for you here, here's my y is equal to 1. We would graph at 1. And then the graph would either look like this or like this. One of these combinations. Whether the graph was y is equal to -3. My horizontal asymptote is y equals -3. I can tell you for sure, -1, 2, 3, ... The graph would eventually either look like the top version or the bottom version. I can tell you the end behavior of the graph. Now, how do we decide what my horizontal asymptote is? It's actually very simple. And the thing is, we just have to remember our 3 possibilities for horizontal asymptotes. So let's go ahead and talk about what our horizontal asymptotes are. Horizontal asymptotes, as we mentioned before, is where the graph eventually will head. What will the graph eventually be? Okay, here's how it is. So any polynomial, any rational function here, rational functions, are made up of a, let's call it a p of x on top. Sorry, actually let's not use p, let's use n. N of x on top for numerator and d of x for denominator. So n is for numerator, d is for denominator. And the numerator is made up of a polynomial as such. Let's call it a1 x to the n plus a2 x to the n minus 1. And this goes on forever. A plus a3 x to the n minus 2, blah, 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 blah. Eventually you get to some number, some constant, some polynomial. On the bottom, we're going to come up with something, we use the letter b this time, b1 x to the, let's use m, plus b2 x to the m minus 1, plus b3 x to the m minus 2, ... So this looks super confusing, right? This is a bunch of letters, but what I'm trying to refer to is this. The top could be some function, 3x squared plus 2x plus 1. The bottom is just another set of numbers, 5x cubed plus 4x plus 2. As you can see, these are just a fancy way of saying the numerator and denominator. And in math, we want to make sure we can write it in a way that generalizes everything. So a number x exponent, a number x exponent, a number x exponent. That's just really what we're doing. We're just staying in a nice fancy way. So I want to ask you, what are the A1 and B1 in this problem. What's A1, B1 in this problem? A1 is 3. B1 is 5. N on top, sorry. The N is 2 and the M is 3. Okay? All this is referring is to the top and the bottom. Top and the bottom. Now, why is this important? Because when I'm looking at a horizontal asymptote, all I care about is the front part of the graph. All I care about is the front part of the equation. I do not care about anything else. I don't care about anything else. If you remember, when we were graphing x squared, let's say x to the fourth plus x cubed plus x squared plus x, when I'm graphing n behavior, do we care about the rest of the problem? No, we just care about the front term, my leading term. That's all we care about when it comes to n behavior. Who's the biggest bully? And that's the same thing here. We only care about who is the biggest bully. And the biggest bully is our 3x squared and our 5x cubed. So for all our horizontal asymptotes, we only care about the front of the problem. That's why it's easy. I'm not worrying about that this polynomial is huge or it's confusing or there's a bunch of negatives. All I care about is that front value. And we'll talk about that in a little bit. Let's go ahead and talk about our first rule. So rule number 1, let's say for sorry, someone just came in the room. Okay, for a polynomial, if f of x is equal to n of x over d of x, meaning I could split this up into a simple polynomial. Okay, if n is less than m, or let's spin this around if you want instead. Some of you guys like larger. If m is greater than n, this means bottom. So I'm running out of space. Bottom exponent is larger. Okay, that's what I mean. If m, looking back here, m is my bottom exponent, right? Isn't my bottom exponent the lower one? If the bottom exponent is larger, then automatically the horizontal asymptote y is equal to 0. This is rule number 1. Okay, so the rule is this. If you look at any fraction, okay, any fraction problem, if you could look at the top polynomial and the bottom polynomial, if the highest exponent is bigger than that of the top, we automatically know our horizontal asymptote is going to be 0. Now let me just demonstrate this real quick. And I'm going to make up a Desmos problem. And I want you guys to look to see if the horizontal asymptote here is going to be 0. That's right, the problem is going to be 3x squared plus 2. Nope. Plus 2. Parentheses divided by, let's do 2x to the, I'm going to use the letter a here. Plus 4. I'm going to give you guys a little trick here. I'm going to change the settings of this by step. We're going to use only positive ones from 1 to 5. Okay, so here's what we're going to do. Right now, this is the a is 1, so that means that exponent is 1. So who right now is bigger, the top or the bottom? You guys agree? The top exponent here is larger, okay? That 2 is going to be larger than the 1 on the bottom. What if I make them exactly the same? Our graph has changed slightly, okay? And then one more. Uh-oh. What did I do here? 2 squared cubed. Oh, sorry. I need to zoom in. How come this jumped to 500? Oh no, why did this jump to 500? Okay. Okay, we're here. That's when a is 1. So this is just 2. Let me write this here so you guys can see it. This is 3x squared plus 2 over 2x1 plus 4. Who's bigger, the top or the bottom? The bottom is smaller than the top. Okay, this doesn't lead us to a horizontal asymptote. What if they're exactly the same? We'll figure that out what happens right now. But what if it's bigger? Easiest one, easy rule in the world. If it's bigger, take a look. The end behavior heads towards 0. This graph eventually will head towards 0. What if it's 4? Still 0. What if it's 5? Still 0. What if it's... Okay, I can stop now. Here is the simple rule. If your denominator has a larger exponent than the top, we automatically have a horizontal asymptote and it's always going to be 0. Now, why is that true? Why can you guarantee me it always being 0? It's actually a pretty cool trick. And let me go ahead and show you guys why. If I give you a simple, very simple example, if I write 3x squared over 2x cubed, okay, we'll call plus 1 here so we don't have to worry about it. Here's our very simple example. Who has a bigger exponent, the top or the bottom? You guys would agree the bottom has a bigger exponent, right? So that's start plugging in numbers. If I plug in 10, if x equals to 10, the top will be 300 plus 1 over 2,000. Wait, that's another. Yeah, 2,000. What's 301 divided by 2,000? Is that a big number or small number? What if I say x is now 100? That's 3, 1, 2, 3, 4 plus 1 over 2, 1, 2, 3, 4, 5, 6. What is 30,001 divided by 2 million? Isn't this even a very small number? So what happens is we end up heading toward 0. And the idea here is that as x gets bigger, who is the biggest bully that's going to win? This guy. So as x gets bigger, I can automatically tell you the graph will head toward 0. But does this work for the negative side? You know what? Let's try it. Let's plug in negative numbers. If I plug in negative numbers here, sure. If I plug in negative 10, x is negative 10. So we have negative 300, no, not negative 300. It's positive 301 divided by negative 2,000. Is 301 divided by 2,000 a big number or small number? It's going to end up as a small number really close to 0, but on the negative side. So what we want to talk about is I can set up the guidelines for the graph by drawing out my horizontal asymptotes, and that will start giving me a framework for what to draw. So let's go ahead and go through our other two rules, and then we can now apply them. Now again, the first rule is the easiest to prove. If the denominator is bigger, okay, if m, which is the denominator, is bigger than the n on top, the top exponent. If this is true, we automatically know our horizontal asymptote is going to be 0. That's an automatic given. Rule number 2. What if the exponents are exactly the same? For f of x, for f of x is equal to numerator on top, denominator on bottom. If m is equal to n, what if both exponents are exactly the same? Then we take our front values, a1 over b1, that is my horizontal asymptote. Okay, is a horizontal asymptote. Oh man, I actually gotta spell this better. Asymptote. Asymptote. If our fraction, our ugly fraction, if our exponents are exactly the same, it turns out a horizontal asymptote is going to be just the front numbers. And what I mean by A and B is, if you remember the way we wrote this, is that we had a and B value. It was just the front of your problem. Now, why is that? Let me go ahead and do this before I show you guys the demonstration of it. If I write 3x squared plus 1 over 2x squared plus 1, do these guys share the same exponent? So I would say they're the same weight. There's no bigger bully here. Your 3x squared and your 2x squared. Now what happens when I start plugging numbers in? What if I plug in 10 and what if I plug in 100? This would be 301 over 201. What do you think happens to 300 and 200? They become 3 over 2. Approximately 3 over 2. Mrs. Go, what about the 1? Does Bill Gates pick up pennies off the floor? My point is that as we head toward infinity, as this number gets larger and larger and larger, do we even care about those small figures? We don't. The biggest bully has taken over. The x squared has taken over. Let's look at the next example. What if I plug in 100? That's 3, 1, 2, 3, 4 plus 1 over 2, 1, 2, 3, 4 plus 1. 100 squared is 10,000. What do you think happens to 30,001 divided by 20,001? Isn't that just approximately 3 over 2 again? And what I mean here is, when we're looking at this problem, is looking at this problem here, the horizontal asymptote would really be right here. It'll be at 3 over 2. And the graph would eventually become 3 over 2. And this graph looks something like that. The graph does not shoot off to infinity. It doesn't go down to 1. It gets stuck at 3 over 2 in both directions. This graph will get so close to 3 over 2, it's painful how close it is. Why? Because they're both runners at the same speed. If you and your friend run at the same speed and you guys are the same type of runner, you guys will never leave each other. 3 can't get away from 2, so we're stuck. Now, did that happen on our last graph, our example here? Did that happen on our last graph, our example here? We said if the exponent was bigger, we would head towards 0. But what if our exponent was exactly the same? X squared, 3x squared over 2x squared. You can look here that we are stuck at 1.5. See how this is getting closer to 1.5? Will this ever get to 1.5? 1.47, 1.48, 1.4. Let's keep on going. 1.49, 1.498. And we're going to get so close to 1.5 that we'll never get there. What happens if I change these numbers around? What if I go ahead and change these numbers around? Call this a 7 and call this a 3. What's 7 divided by 3? Isn't that 2 point something? Check it out. We're going to become closer to 2 point something, 2.3. Will we ever actually touch 2.3? Nope. Not because of that, of these leftover children here. See this 2 and see this 4? These numbers here prevent it from being exactly 3 over 7. It's a little bit off. It's almost like there's a dent in your car. It's never going to be perfect anymore. So our rule is this. No matter what the graph looks like, I can tell what the horizontal asymptote is by memorizing these 2 rules. We have one more rule. And the rule is this. The last rule is this. What if we said the bottom was bigger? Here, the rule 1, the bottom is bigger. Rule 2, they're exactly the same. Rule 3, what's rule 3? Rule 3, and hopefully you can guess, is what if the top exponent is larger? Okay, What I mean is, what if it's x cubed over x squared plus blah, so blah, 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 okay? Plus blah, blah, blah. And when we're graphing these graphs, we don't care about the everything else. We just care about the biggest bullies in the front. What happens when the top is bigger? We have no horizontal asymptotes. There is no special asymptote when the top is bigger, except here's a special rule. This is an exception. Whoops, haha. Except when n is bigger by 1. If n is equal to m plus 1, that means that if n is bigger just by 1, just like what we see here, we have a slanted asymptote. And we'll talk about what a slanted asymptote is later, but today we're only going to focus on a horizontal asymptote. Now I'm going to give you a bunch of examples very quickly, and you're going to tell me what the horizontal asymptote is. Okay, here we go. So we'll do 1, 2, 3, 4. Okay, problem is x cubed plus x squared plus x over x to the 4th plus 3x. This is my graph. Y is equal to, what is my horizontal asymptote? Y is equal to what? Second problem, y is equal to 2x squared plus 5x over 7x squared plus 3. What is my horizontal asymptote here? Next problem, x to the 4th over x to the 6th minus 7x squared. What is my horizontal asymptote here? And 7, I keep saying 7, right? Oh, 7x to the 3rd plus 2x divided by 1 minus 4x cubed. Here are 3 problems that will illustrate if we know what my horizontal asymptote is. So I'll give you guys a moment to copy them and to see if you can figure out what my horizontal asymptote is. Now be careful. We're looking at the largest exponent, so I'll highlight that for you guys so you guys can see it. My largest exponents, my largest exponents, my largest exponents, and my largest exponents. So be careful when you're looking at what is my largest exponents. So first question here, is the top exponent bigger, the bottom exponent bigger, or are they exactly the same? Those are our 3 conditions. Hopefully you can see that the bottom exponent is a 4, the top exponent is a 3. These are the biggest bullies in each lot. The biggest bully is the bottom. So our rule is, if the bottom is bigger, you are eventually going to end up at 0. Again, why is that? If I say x cubed over x to the 4th, as x gets bigger, the bottom will kill the top. The bottom will murder the top when it comes to numbers. And numbers on the bottom, when they're bigger, we always end up going to 0. Okay, that's the reason. Take a look at question number 2. Are the exponents the same? Is the top bigger, the bottom bigger? If you notice that the exponents are the same, our horizontal asymptote is simply just 2 over 7. That's it, 2 over 7. Why is it 2 over 7? If I say 200 divided by 700, isn't that just 2 over 7? But just go, what about the 5x and the 3? Nobody cares about it once the numbers are big enough. If I say 2,000 over 7,000, what is 7,003 going to matter? It's not. That's why it's about 2 over 7. What about 2 million over 7 million? The millions cancel out. The rest is just small decimal places. Look at number 3. Is the top bigger or the bottom bigger? 4x squared on top and 6x, no, x to the 6th, oh my gosh. X to the 4th power on top and x to the 6th power on the bottom. The bottom is bigger, So we know this is automatically going to go to 0. And our last question here, I wrote this in the wrong order, not largest in the front, but hopefully you caught it. It's that since we're looking only at the largest exponents and they're exactly the same, what is 700 divided by negative 400? Those cancel out to become negative 7 over 4, no matter what values we plug in, as long as they're sufficiently large enough. Okay, so that's how we're going to find our horizontal asymptotes. That's what it's going to ask you for on your homework today. And once we understand how to graph vertical asymptotes and horizontal asymptotes, we're right. Our next step is to actually graph the graph with minimal effort. With minimal effort. That's why if I give you a graph, like what we talked about before when we first started, our graph was, what was it? 1 over, let's graph then this graph. If I say graph y is equal to 1 over x squared minus 4, I am already one step ahead. We said this already, plus 2, x minus 2. We know our zeros. So step 1, find our vertical asymptotes at negative 2 and 2. All right, on my graph, negative 2, positive 2. We know we can't work here already. Step 2, what is my horizontal asymptote? We know horizontal asymptotes are going to be, hey, what's bigger, the top one or the x squared? The x squared will be bigger. So our horizontal asymptote y is equal to 0. So we know the graph is going to be going towards 0. So I draw my next line here, 0. Now all you have to do now is test the graph on the 3 sections. If I plug in a number that's really big, bigger than 2, that's plug in 3. Plug in 3, plug in 3, that's positive. We are for sure on the right going to infinity. Oh my goodness, how did you know that, Mr. Ko? It's because if I draw a line here, I get stuck at this wall, don't I? So it gets bent up. And if I get stuck over here, we know it's going to curve out. So it's going to curve over this way. Let's look on the left side. If I plug in negative 3, see negative 3 is next to my 0. If I plug in a negative 3 and negative 3, this becomes negative. This is also negative 3 and negative 2 and negative 5. What's a negative times negative? Still a positive. We know our answer is going to be on top. We're going to be up on top up here. The left side will always be stuck in that corner. What happens in the middle? Plug in a number in the middle. I see 0. 0 is an easy number in the middle. That's plug in 0. 0 and 0. That's 1 over 2 times negative 2. That's 1 over negative 4. We know we're negative here. I can guarantee you the graph is going to look like this. 900%. Did I need a calculator? Nope. And that's our skill that we're building to. Let me go ahead and graph this one more time for you. If I do end up graphing that same graph, 1 divided by x squared minus 4. Take a look. That graph looks almost exactly like the graph I did. Okay? And that's our stretch goal, you could say. All right, that's it for today. Our practice for horizontal asymptotes.